Hello and welcome to another me explaining through some maths from the A-level specifications. Today I'm going to be looking at mechanics, specifically the hinges section of static rigid bodies in the second year Edexcel mechanics unit. Problem with this, at least the textbook that we have doesn't cover this particularly well, so I just wanted to go through some examples to explain what's going on. So we're going to look at this example here. Apologies for the shadows, but I'm trying to do the best I can. Right, so we've got that here we have a sine of weight 400 newtons hanging from the end of a uniform rod. Rod is 4 meters long and weighs 600 newtons itself. Okay, so it's not light, but it is uniform. The rod is supported by a hinge at the wall and by a cable whose other end is tied to the wall at a point 3 meters above the rod. Find the tension in the supporting cable and the force of the hinge on the rod. Now, the thing that makes hinge questions difficult, or potentially more confusing, is labeling the forces. Clearly, we have our weight of the sine. Okay, careful, it's mass, not weight. We also have the weight of the rod. Somewhere in there, that's 600 newtons, and we know that this distance is 2 meters because it is uniform. Okay, remember, uniform means that the weight acts on the middle. We also have tension here, and this angle theta. Okay, that may or may not be relevant, but let's label it anyway. Now, the thing that makes the hinge questions difficult is a lot of people go, oh, there's a point of contact here, which means there's a reaction force horizontally. The problem is there's also forces here which have a vertical component. If there's no vertical force here, then the hinge is going to fall, or the sine is just this bit here, which we know is attached, is just going to slide down. So there has to be a vertical reaction force, which I call Ry. R for reaction, Y because it's vertical. There's also a horizontal reaction force acting there, because otherwise the stick, the rod, is just going to go through the wall, which we know doesn't happen. So this is the thing that makes it difficult. Now, clearly, we're going to need to use some trigonometry here because we've got triangles. We're not told what theta is, but we know this triangle is a 3, 4, 5 triangle. Okay, so we've got 4 meters, 3 meters, and 5 meters, which means that sine theta is going to be opposite over hypotenuse, and cos theta is adjacent over hypotenuse. So we don't actually need to work out what theta is. So what we need to do is we need to think about moments in order to find the tension. Let's take moments about the hinge. Why do we do that? Well, so that we can ignore the forces acting here, which we don't know. Okay, so we're going to take moments about the hinge. So we know, because we can see, that the two weights are going to cause a clockwise moment. Okay, so we've got 600 times 2, force times perpendicular distance, and 400 times 4. Okay, this is held in equilibrium, so we know the clockwise moments are equal to the anti-clockwise moments. Okay, now we know this force is T, and we need to find the perpendicular distance from T to the rod. So I resolve distances, you could resolve forces if you wanted to. Okay, so we want this distance. This distance is 4 sine theta, which we can see is going to be 12 over 5. Okay, so we now know that 1200 plus 1600 equals 12 over 5 times t. Thinking about it, we should probably do a little bit more working. So we've got times 4 times 3 over 5, just to show where that 12 over 5 comes from. So t is going to be 2800 times by 5 over 12, okay, which is 1166.67 newtons. So to three significant figures, T is 1170 newtons. So that's fine, we now know T. So we can use resolving forces to find these reaction forces. So let's have a look back at the question. Find the tension in the supporting cable. Done that. And the force of the hinge on the rod is the resultant force of these two. So the force we're trying to find is the square root of ry squared plus rx squared. That's all we're trying to find. The resultant force of these two forces. Now we can see we've got one force horizontally and the horizontal component of T. So let's just resolve T here, just so it doesn't get in the way. Okay, so here's theta. This is T opposite sine theta, and this is T cos theta. Okay, T is going into the wall, or towards the wall, so this is going up and across. So we resolve. So we resolve horizontally. Rx is T cos theta. So nice and simple there. Okay, which is going to be 66.67 times cos theta's 405. Okay, so that is going to give us 2,800 over 3. Now I'm keeping this exact as opposed to rounding because we're going to use this later. Okay, this is not part of our answer. We are using this later. Okay, so now we're going to resolve vertically. This one's a little bit trickier because we've got a bunch more forces. So forces up is Ry plus T sine theta. Forces down, 600 plus 400. Okay, so we know Ry is 1000 newtons minus T times sine theta, which comes out nicely to 300. Okay, so these are the components of this resultant force on the wall. So last thing we need to do is find that force. So the resultant force on the wall, sorry, on the rod, not on the wall, is 300 squared plus 2,800 over 3 squared, all square rooted, which comes out to 980 newtons. Okay, generally that's how hinge questions work. Sometimes you might have to change the sign of these, and that's all the direction of these, and that's fine, because all that it means, if you pick the wrong direction, it's not the end of the world. All it means is that your answers here will come out as negative. So you know, for instance, if we'd chosen Rx as left instead of right, this would have been minus. 2,800 over 3, no big. Okay, so that's our first hinges example. Our second one is a little bit more extensive, so bear with me. Because as you can see, we have slightly different forces. There we go. Okay, conveniently this time we've been given these. So I tend to call them Rx and Ry. You can really call them whatever you like. But notice here we have P, our pulling force, going in a different direction. On the previous example it was this way because we were simulating a sign being held up to a wall by a rope or a chain or something like that, or even a stick like a metal rod or something like that. But now what we've got is a force pulling it. Okay, it's still pulling up. Here's our hinge. But effectively, we do exactly the same thing. We just need to be very careful with our directions. So we're told the uniform rod again, so it's uniform, which is great, because that means that the weight is in the middle. It's mass 10, so we know the weight is 10g. And we know that this distance is 2 meters. And we know this distance is 2 meters. Okay, so same thing again. We can use moments about the hinge here to work out our force P, and then we can resolve forces to find x and y. Again, we've been given the direction of x and y here. If we weren't and we picked the wrong direction for x, it's fine, because all it means is our answer will be minus. We can see though that the reaction force is into the wall, because if it wasn't, the whole thing would just move off the wall, because we've got this pulling. So there has to be an opposite force holding it to the wall. Okay, so but this time we want the angle of the line of action, because the thing is, this force, when we resolve it, does something like that. So we're trying to find this angle here, eventually, but we'll get there. Okay, so first things first, moments about the hinge. This time we're given the name of the hinge, it's A, so we can just say moments about A. So we've got clockwise moments and anti-clockwise moments. So this time we could resolve, so again we could resolve the force or the distance. This time it's easier to resolve the force, okay, because that's the one we want. This one here, okay, because the force is attached to the end here. For me, that just makes more sense. You could still resolve the distance and have kind of that'd be the perpendicular distance. This time it's easier to resolve the force, because spotting where the shortest distance from the pivot to the force is a little trickier. Okay, so we need to resolve the force. So this is the one we want. We know that this is 40 because of z angles. So this force here is going to be P sine 40, and then we times by the length. So we can see that 20g is 4p sine 40. So P is 5g over sine 40, which comes out as 76.230 and a bunch of some other numbers. Okay, so to 3 significant figures, 6.3 newtons. Now, I know technically with this one, we should only give our answer to 2 because we are using g to 2 significant figures. The textbooks do this. my understanding is if you leave it to 3 significant figures, that's fine. You can generally get away with it. Anything more than that, you'd start to risk losing marks for not rounding appropriately. Now we know P. If you particularly want, we didn't on the last one, but you can if you want, change the diagram. Now, if the diagram is part of your question, so if it was part A, draw a diagram, don't change it. But here we were given the diagram, so it's no problem. Okay, it doesn't form part of our answer. So, like before, we resolve forces. Again, horizontally. So we've only got 2 forces horizontally, x and this horizontal one here. So we know x equals p cos 40, or sine 50 if you prefer. So we know x is 76.2 and some other numbers times cos 40, which comes out as, to 3 significant figures, 58.4 newtons. Resolving forces vertically, we've got y and this p sine 40, and that's equal to 10g. Oops. Okay, so y is 98 10g minus 76.2 sine 40, which comes out as 49 newtons. Okay, so now we want the magnitude of the reaction force, so size. Okay, it's going to be 49 squared plus 58.4 squared, all square rooted, which comes out as 76.2 newtons. Lovely, same as P. That's, for this example, probably not coincidental. I'm not sure, but there we go. Okay, last thing we need to do, work out the angle it makes with the wall. So we can see from our diagram above, we've got our x and y, this here, so that's x. So opposite over adjacent, tan theta is x over y. Okay, whoops, that's like I said, y. Okay, so we've got 58.4 over 49, which comes out as 1.19. So theta is inverse tan of that, making sure we're in degrees mode, which comes out as 50.0 degrees to 3 significant figures with the wall. Okay, we always measure with the wall because that's, well, if the force like this one is going into the wall, we always measure with the wall because there's no other kind of permanent physical thing that we can measure it with. If, like with the previous example, we were acting out here, the reaction was here, we could do the angle with the wall or angle with the rod. Here there's no physical thing for us to measure against, so we use the wall. Okay, last example. This one is basically, if you can do this one, you can do all hinge questions because, well, this one's quite complicated. So we have a uniform boom shown in the diagram weighing 700. I'm just going to zoom in as best I can. There we go. Okay, we have a uniform boom shown in the diagram weighing 700 newtons. Okay, the object hanging weighs 400 newtons, so we've already got its weight. The boom is supported by a light cable and by a hinge at the wall. So, again, let's do some labelling of forces. Tension, 400 newtons. 700 newtons. We know here there's a reaction force horizontally and a reaction force vertically. What else is going to be quite useful is this angle here, potentially. But we can see that that's going to be 20, again, from Z angles. You can label that if you want, or just recognise it later. Ooh, is that making it better? No, that made it worse. Okay. There we go. Okay. So, again, this time the boom is uniform, so we don't have to worry about distances. The problem is that we don't have any lengths. But if you've paid attention to the other ones, quite often you'll find that the length cancels out. So it tends to be sometimes can be independent of weight, of the length. So let's just assume the boom is 2A meters. We could choose anything we like. If we choose an even number, so 2A, that means that this distance here is A, and it just makes life easier for ourselves. So, same again. You'll notice there is a repetition here, moments about the hinge, to find this force. Okay, so if we take moments about the hinge, this is where things get a little complicated. Okay, because we've got the booms at an angle. So again, I'm going to resolve distances. You can resolve forces if you prefer. Okay, so this distance, this is 2A, this angle's 65. So this length here is 2A sine 65. This distance here, because we're going to need that one in a moment, is A cos 20. And this distance here is 2A cos 20. Now I know my diagram's got quite crowded, but that should be all the information on it that we need. Okay, so we can see here this is going to cause an anti-clockwise moment. So we know that T times 2A sine 65 is going to be equal to the clockwise moments. 700 times A cos 20 plus 400 times 2A cos 20. Now again, I know I could put 800 here, but I'm clearly showing that I understand force times perpendicular distance. Okay, if you put 800 A cos 20, that could be a little misconstrued, so just be careful with that. Can you now see why this doesn't matter? All of the A's cancel. So we get that 2T sine 65 is 700 cos 20 plus 800 cos 20. So T is 1500 cos 20 over 2 sine 65, which is going to come out as 777.63 and some other stuff, newtons. Okay, so that's the first bit of part A. Calculate the tension in the cable. Done that. Tension in the cable, done. And the magnitude of the reaction at the hinge, well, we know how that works. Find Ry, find Rx. How do we do that? Same thing as we've always done, resolve forces. Okay, so resolve vertically, changing it up. So we've got now here, this bit is T cos 45. Sorry, T sine 45. Is plus Ry equals 700 plus 400. So Ry is 1100 minus 777.63 sine 45. Nice. Okay, which comes out as 550.13 and some other stuff. We resolve horizontally. Like before, we've only got two forces. We've got Rx and the horizontal part of T. Rx equals T cos 45. Oh well, doesn't matter. I mean, it does in terms of getting all the marks, but you know, these are the same thing. So Rx is going to be, there we go, 777.63 cos 45, which comes out nicely as 707, oops, sorry, darn it, 549.87 newtons. So therefore, the reaction at the hinge equals 549.87 squared plus 550.13 squared, all square rooted, which comes out as 777.8. So to three significant figures, 778 newtons. So very similar, but slightly different, which is interesting. Okay, so I should probably give that to three significant figures as well. Okay, so that's all the calculations for part A. We've got the tension and the reaction of the hinge. So part B, let's look back up, whoops. Explain how modelling the cable as light affects the model. Well, that's just understanding what light means for mechanics. Light means the cable, the weight of the cable is not considered, or is considered as part of the model. So you could model the weight of the cable as part of the rod if you fancied it, but we're not going to. So we just say the weight of the cable is not considered. And we're done. So that's three examples of hinge questions. Realistically, if you can follow this one and understand, or just remember that the reaction of the hinge has two bits, then you should be fine. Sometimes, very rarely, but sometimes, you might find that one of the components, X or Y, comes out as 0. That's fine. All it means is that the reaction forces entirely vertical or entirely along the rod. If that happens, then oh well, it just happens. But don't assume that that's a thing that's going to happen. More likely, it's going to be this kind of thing. Okay, but there we go. So that's a few examples for hinges. I'll probably do another video going through some pure question examples shortly. I'll try and put that up maybe next week, but we will see. Again, if you've got any requests or any questions, please put them in the comments, and hopefully that makes sense. Thank you. Bye.